acids and bases. So to start off with, before we delve into this, I want you to ask yourself, when you hear the word acid, what do you think of? When you hear the word base, what do you think of? So think about that for a second. We start looking into acids and bases. We have various different properties of our acids and bases. Acids are sour, bases are bitter, basic solutions have a really slippery, soapy feeling to them. Acidic solutions make litmus paper red, basic solutions make litmus paper blue. When we look at pH, acidic solutions have a low pH below 7, basic solutions have a high pH above 7. And then when we do a neutralization reaction, they react with each other to give salt and water. Okay, so here's a lemon and some ammonia, and you can see on the litmus paper, the base turns it blue, the acid turns it red. So these are some really common acids. There's a ton more acids than these. These are just some really common acids. There's citric acid, hydrochloric acid, sulfuric acid, acetic acid. Does anybody know what acetic acid is commonly? You probably have it in your kitchen. Acetic acid is also known as vinegar, all right? And it can also be written like this. Okay, so both of these, same formula, they're just different ways of writing them. Because acetic acid falls under this, it's what is called a carboxylic acid. And so all these carboxylic acids have this group right here. And so when you write it, that's COOH, this is what you're writing right here. And then this hydrogen is the one that is acidic and comes off. We have three different definitions we can look at acids and bases with. There's our classical or Arrhenius definition, the Lewis definition, and then the one that we are going to look at in most detail, our Bronsted-Lowry definition. So our classical definition just looks at whether or not we have something that yields a hydrogen ion or a hydroxide ion. Now, we get these two things are used interchangeably, all right? H plus and H3O plus, basically, when we talk about acid-base chemistry, they mean the same thing. This is the acidic portion of it, all right? H plus is known as a proton. Because remember, hydrogen has one proton and one electron. Well, if we get rid of the electron, all we have left is the proton. And so a hydrogen ion is just a proton. All right, so again, in our classical definition, we're going to get our H plus or our hydronium ion. Oh, and something went wrong and didn't show up. This should be a minus. Gotta love when PowerPoint doesn't always cooperate. So we should get that A minus. So this is HA is just our generic formula for an acid. Okay. And then bases give us that hydroxide. Oh, and again, it's not giving me my negative charge on them. So there we go. All right. So we get our hydroxide in solution. Lewis, we're not going to work with this so much, but basically a Lewis acid base, we look at electron pairs. So an acid is an electron pair acceptor, a base is an electron pair donor. All right, and now we're going to look at Bronsted-Lowry. So acids are proton donors. So acids are going to produce that H plus ion. So we have to have an acidic hydrogen or an ionizable hydrogen in the formula. A base is going to be a proton acceptor, meaning it has to have a spot where that H plus ion can come and attach to. Okay, so here we can look at a few things. So water can act as an acid or a base. So in our first example here, we've got hydrochloric acid. So our water has a lone pair of electrons on the oxygen that can accept the hydrogen off of the hydrochloric acid. And then we get the chloride ion and the hydronium ion. Okay. Ammonia has a lone pair of electrons. It can bind a hydrogen coming off of water, gives us the ammonium ion and then a hydroxide ion. When we look at our Bronsted-Lowry, we have conjugate acid-base pairs. So our reactants are going to be our acid and our base. And then our products are going to be the conjugates. So an acid will have a conjugate base. A base will have a conjugate acid. So when you're trying to identify them, you look for the species that are similar. So here I have H2SO4 and HSO4. So I've got a sulfur here and a sulfur here. So those have to go together. So sulfuric acid and then that hydrogen sulfate. So my sulfuric acid is my acid and the hydrogen sulfate is the conjugate base. And then water accepted a proton. So water acted as my base and then the hydronium ion is my conjugate acid. Okay, so you can see a few more here. So ammonia is the base, so it's got the conjugate acid of the ammonium ion. Water is the acid, hydroxide is the conjugate base. Okay, so here I have a whole bunch set up. You can see the acid and the base, and then this is the conjugate base, and this is the conjugate acid. So I abbreviate them. I don't like to write out conjugate all the time. So I would say this is the acid, this is the base, here's my conjugate, my conjugate base, and my conjugate acid. Okay, here I have another acid, so I have my conjugate base, here I have a base, and my conjugate acid. Okay? So here's two for you to look at. So I want you to pause and I want you to see if you can recognize which species on the reactant side had one more proton and then its corresponding species on the product side that had one less proton. And then which species on the reactant side had one less proton corresponding to a species on the product side that had one more proton. Okay, so pause and see if you can identify these. All right, let's see how you did. So I have this dihydrogen phosphate and I have a hydrogen phosphate. So I went from 2 hydrogens to 1. So I lost it. So acid's my proton donor. So this has to be my acid. This becomes my conjugate base. All right. And then my base is my proton acceptor. I went from carbonate to hydrogen carbonate. So I gained a proton. So base and its conjugate acid. Okay. When I go down to the second one, water had H2O down to hydroxide, so I lost a proton. So acid, conjugate base. And then I had the sulfite anion that went to hydrogen sulfate, so it accepted a proton to base and its conjugate acid. Okay? All right, so when we look at these, our Arrhenius definition, our acid forms H plus in solution, base forms hydroxide, Bronsted-Lowry, acid's a proton donor, base is a proton acceptor, and then that Lewis has to do with the electron pairs, and we're not going to delve too far into that, but I wanted you to be aware that there were 3 different ways that we could define an acid and a base.